This session, the first speaker is Sitan, Chen. Sitan got to speak to MIT.
Thanks. So yeah, I'm looking forward to spending the next few years as a postdoc here at Berkeley. Today I want to tell you about some of the things I've been thinking about over the last few years regarding what algorithmic insights from TCS can tell us about modern challenges in data science. Now, this turns out to be a fairly subtle endeavor because of a fundamental disconnect between the way we traditionally reason about algorithm design and the kinds of problems that arise in data science applications. Let's take something like max flow. The gold standard we're taught is that we should have an algorithm that, if you fed it an arbitrary worst case instance, correctly spits out a max flow after running a polynomial amount of time. And by now, we have a fairly mature understanding of which problems on this map you can hope to achieve this gold standard. For instance, SAT solving or graph coloring. And which questions, for instance, SAT solving or graph coloring, for which it's likely to be impossible. Now, you can draw a similar looking map for problems in data science. But actually, through this traditional lens of worst case analysis, a more accurate depiction would be something like this. And the reason is that most ML problems, if posed from this worst case perspective, are just hopelessly hard. So to get actionable theory for machine learning, it's not enough to just develop the right algorithmic primitives. You really need the right mathematical models to go along with them. This begs two questions, which have been the focus of my work. First, have we converged to the right toolbox for dealing with fundamental problems in data science? And two, are we looking at the right models? In this talk, I want to tell you about some natural settings where new techniques are provably necessary, as well as instances where working with the right or wrong model can have consequences far beyond the realm of theory. In the course of advancing this viewpoint, my research has touched upon most of the regions on this map. But in the interest of time, I want to hone in on my work in one particular area, namely the design of algorithms that are robust to any number of real-world deviations in your data. Okay, so to unpack what I mean by robustness, let's talk about some of the common challenges that arise in working with modern data sets. Okay, so it's a fact of life that modern data can be extremely high dimensional. It can be very heavy tailed. For instance, if you plot how often different categories of objects appear in standard scene recognition benchmarks, you'll find many categories with a very small number of occurrences. When it comes to things like online reinforcement learning, data can be generated in a dynamic non-IID fashion that may even depend on the actions you choose. And data could be misspecified, in the sense that there's a disconnect between the setting where you know that your ML system works, the spec, and the setting where you actually want to deploy it. So for instance, your spec could be some great theorem you proved about learning over linearly separable data. And reality could be that the data set in the wild that you want to apply your algorithm to simply doesn't satisfy this assumption. The spec could be the traditional end-to-end supervised learning pipeline. And reality could be that there's an adversary that's able to tamper with some fraction of your data, for instance, in the context of a data poisoning attack. Now, my work is focused on designing new algorithms for basic learning problems to meet these kinds of challenges. And for the sake of concreteness, I want to tell you about one very recent result of ours, joint with Fred Kohler, Ankur Moitra, and Morris Yao, that seeks to address all four of these challenges simultaneously. So let me just tell you sort of one nugget from this paper. Just consider the standard setting of linear regression, but with the following twist. Let's imagine that a random but constant fraction of the data has been arbitrarily corrupted. Okay, so just to recall the standard linear regression setup, we get xy pairs where the y's are noisy linear functions of the x's, where the linear function is parameterized by some vector w. Let's adopt some standard scalings. So let's say that the x's are normalized, have unit norm, and w has norm at most r, where you should think of r as like the dynamic range of the problem. And we can imagine the noise as maybe coming from a Gaussian with variance sigma squared. And here we should think of sigma as being significantly smaller than r. Okay, so this is just standard fixed design linear regression. Now let's imagine an adversary comes along and is able to tamper with a randomly chosen 10% of your data. So in particular, this adversary you can imagine as being all powerful. It inspects, it has access to the full data set and can run in as much time as she wants. And eventually they're going to change these y values to whatever they want. And we as the learner only observe xy pairs. Okay, so what's our objective here? Our objective is to compete with the all-powerful baseline, which actually knew exactly which points were corrupted. Because if you knew which points were corrupted, you could, of course, just throw them out of the data set and run ordinary least squares on the rest of the data. And the objective we want to minimize is what we'll call the clean mean squared error. Roughly speaking, this is the average squared distance between your prediction, which is w hat inner product x, and the ground truth label without noise, w inner product x. Let me emphasize that while there have been a number of exciting recent works on robust statistics in high dimensions, the model that I've just described is sort of a departure from these works in the sense that we're not making any kinds of strong assumptions on the process that actually generates the xi's. In particular, not only could they be IID from some arbitrary distribution, these xi's could actually arrive in some adaptive fashion. Okay, so what do we show? So one result from this paper shows that for any value of corruption from 0 to 1/2, we give an efficient algorithm for this Huber-contaminated regression problem that achieves clean mean squared error, which is essentially optimal up to log factors. And because our algorithm is able to tolerate adaptively chosen covariates, we're actually able to get extensions to challenging online problems. For instance, we get the first algorithm for linear contextual bandits that's able to handle a constant fraction of the time steps being corrupted. And the regret that we achieve in this context is also optimal to log factors. To complement these results, we also show that you can't actually achieve these kinds of guarantees using off-the-shelf techniques like gradient descent to minimize a convex loss, for instance, minimizing the L1 loss or Huber loss. And so at this juncture, let me tell you a bit about the algorithm. The nice thing is that the analysis is a bit tricky, but the algorithm itself is very simple to state. So we're going to minimize this notion of squared error over vectors W hat and simultaneously over subsets of the data set. So here you should think of the subset S as our guess for which points in the data set have not been corrupted. Okay. And this S we're in the optimization is going to range over some family of large subsets of the data which behave quasi-randomly, and the technical details aren't happy to talk about offline. But the algorithm, once we have this in place, is quite simple. So we initialize our guess for which points aren't corrupted to be all points. And then we just repeat the following. I keep S fixed and I refit W hat. Then I keep W hat fixed and I refit S. Okay, so you can think of this as just some kind of alternating minimization procedure. And the point is that after you run this for enough steps, you converge to an approximate stationary point for this objective. And the key structural result, whose proof I won't tell you about, is that an approximate stationary point for this problem suffices to achieve this near optimal clean mean squared error guarantee. Okay, in the remaining time, let me tell you about one experiment in a related setting on real world data. So in a different paper with the same set of authors, we explored sort of the analogous setting for classification. So here the Y values are binary labels instead of real valued. Okay, and for instance, the model that we considered captures learning half spaces with Mozart noise. The algorithm that we consider turns out on the surface to be quite similar. It's also based on some kind of iterative reweighing of the data sets to mitigate the effect of corruptions. Let me just tell you about the experiment. So we ran our algorithm on the UCI adult data set. Here, the task is given the demographic info for an individual, tell whether they make more than 50K. And we injected into this data set a particular attack. The details aren't super important, but suffice it to say that we're targeting a specific subpopulation of the data. And so you can think of it as injecting noise, but in a heterogeneous fashion into the data set. Okay, so what happens if you train on this noisy data? So we compare it against 3 different baselines, random forest, logistic regression, and minimizing a particular convex loss. And as you vary the noise rate on the x-axis and look at the resulting classifier that you get out of these algorithms, you'll notice that they do fairly similarly if you measure the accuracy over the entire population. But if you restrict your attention to, for instance, people in the target group who do make more than 50K, then you see a significant degradation in the performance of classifiers obtained by logistic regression and this convex loss as the noise rate increases. Okay. In fact, this phenomenon is quite robust across different kinds of subpopulations. And this is just some empirical observation, but it suggests that perhaps being robust in richer noise models isn't just some kind of mathematical exercise. It really helps guide the design of better algorithms downstream. Okay, so in the remaining time, let me just briefly mention some other things I've worked on. So it turns out this general blueprint of iterative reweighing schemes has also been useful in my work on secure distributed learning. And even in more traditional learning theory settings where you actually assume the data might come from some nice distribution like a Gaussian, and you're trying to learn some complex function class like neural networks. Here, the idea of carefully reweighing the data turns out to be useful even in these non-robust settings, for instance, yielding the first example of a neural network class that you can learn efficiently, but provably not by noisy gradient descent on a student network, for instance. I've also worked on mixture models. This is like a stylized model for heterogeneous data. So I've worked on a sort of heterogeneous variant of robust linear regression. latent variable model called mixtures of product distributions. And turns out related ideas for learning mixture models have also been useful for settling some old debates in the natural sciences. So in classical optics, for instance, by rephrasing the problem of optical resolution as a mixture model learning problem, we were actually able to refute the longstanding belief that half the wavelength of light marks the point at which optical resolution becomes impossible for classical systems. Among other inverse problems in the sciences, I've also worked on quantum learning, where even the sample complexity for various basic learning tasks remain open. Here, it turns out that tools from showing lower bounds for online decision-making actually are a perfect fit for showing separations for learning with and without quantum memory for a variety of tasks like shadow tomography, state certification, et cetera. And more broadly, I'm interested in TCS as a whole, and I've spent some time also thinking about algorithms for counting and sampling. Here are some questions that I'm very excited to think about over the next 2 years. If any of these pique your interest, please do reach out. It would be great to collaborate. Thanks.
Question by William.
Why do you think random forests do so well in the experiment?
Yeah, I always get this. Yeah. So for a bit of context, I guess the one baseline, like theory baseline that we're trying to sort of improve on was this improper learner of Diacono-Colas et al. And even though the algorithm is quite different from random forest, you can kind of think of both as trying to find some partition of space and sort of classifiers that do well over these different parts of the partition. So in some sense, we were trying to get some kind of simple classifier that is able to match the spaceline. And it stands to reason that maybe like algorithms that partition up the space in different ways might be able to mitigate this this kind of violation of the quality of opportunity that we see. Yeah, great question. Okay, thanks.